Thank you so much for this lovely introduction. I'm very excited to be here. It's been a great day so far. I hope everybody got some dinner, didn't get too many beers, because we're going to dive into some fairly low-level mathy stuff, so please bear with me. As I said, my name is as Stefan said, my name is Franziska Hinkelmann, and I'm a software engineer on the Chrome V8 team, and I'll talk about performance profiling for V8. So V8 is the JavaScript engine in Chrome. So I think we can all agree that it's pretty amazing what JavaScript can do. It's not only what it can do, but also how fast it can do it. Felix said a few times in his last talk, oh, if you want something that's critical to performance, you need to go native to C++. Yes, but even if you don't go native, JavaScript can do a lot. Like compared to where it was 20 years ago, you can run pretty massive things with JavaScript and still have good performance. You can run enterprise node servers or all these websites with those huge complex frameworks like what Facebook is using, or if you look at YouTube, like this would not have been possible with JavaScript from the beginnings. So yes, C++ is still faster, but JavaScript has come a really long way. And of course, this performance comes down to the underlying JavaScript engine that is running your JavaScript code. So in this talk, we'll look at what V8 does to give you this good performance, what optimizations V8 does to JavaScript, and how you can profile or trace the optimization steps in V8. A little bit of context here, since I keep saying, oh, V8, V8, V8. If you might not need to care about what your underlying JavaScript engine is and not have heard about V8 before, but V8 is a JavaScript engine, so that means when you write source code, you have some JavaScript source code, you need something that turns whatever you write into machine code that's being executed. And that's the JavaScript engine, or called virtual machine. V8 is not the only JavaScript engine. All the major browsers have their own engine. So there is Chakra Core, that's in Microsoft Edge, open sourced recently, last year. There's JavaScript Core in Safari, there's SpiderMonkey in Firefox, and then V8 is what you have in Chrome. But we know JavaScript, there's more places than just the browser where you find it. So obviously there's Node.js. By default, Node comes with V8, but you can install a node that has Chakra Core as its engine. And then we saw Felix's great talk on Electron. It relies on Node and Chromium, so also in there you have a V8 engine hidden. And then there's other engines for different use cases. So on an IoT device, size is important, so you're probably willing to trade performance for size. You don't need a full-blown V8 engine that is very fast, but also it's pretty big. There are things like duct tape or Samsung's JerryScript, which run JavaScript. They're not as performant as the bigger engines, but it's much smaller. And since I'm on the V8 team, everything I say will be specifically for V8. So if your code runs in Chrome, or if you have a Node app or Electron, then it's V8. Okay, and in order to talk successfully about performance profiling, we need to define a few key concepts in V8. So we'll look at what just-in-time compilation is, inline caches, the optimizing compiler, and we'll even look at some machine code. And I'm hoping to give you some insights into the inner workings of V8, so that this engine that's executing your JavaScript code is less of a black box and you feel you have some idea of what's going on. And then I'll show you a bunch of tools that you can use to profile, or mostly we call it trace, what's going on inside V8. So those are tools that we use internally on the team to figure out what is V8 doing. Is it fast enough? Is it doing something weird? Why is this slow? So a bunch of tools we need internally, and then once we have figured out what exactly is going on or where we need to focus, we can make changes to V8, which then go into Chromium and execute your code. But you can also use these tools to see what's going on in the JavaScript code that you wrote, and then not make the changes in V8, but maybe change the JavaScript code because you see, oh, if I call it this way, V8 is not understanding it and is doing something with a lot of overhead that's slowing me down. So it's tools for us internally to change V8, but it's also tools to change JavaScript if you really, really care about performance. Okay. In Chrome Developer Tools, when you look at JavaScript code, you can create a profile. So everybody knows Chrome DevTools. You can use the console and inspect your website. But there's also a profiles tag where you can record a profile of the JavaScript that you're running, be it from a website or also from a Node application. And so here I've recorded a CPU profile of a TypeScript run. And from the profile, you see, okay, these functions take up a lot of time. If you've ever done anything with performance, you've probably looked at that and then decided from that where you should focus your efforts or figure out what looks weird. But one thing you notice here is there's a few functions on here that have these warning exclamation signs on them, the little yellow ones. So, for example, is related to sticks out here because it's warning, there's an exclamation mark. And when you hover over that, it says not optimized, optimized too many times. So clearly something is going on. The profile or developer tools feels the need to tell us, be like, whoa, warning, something is here. And we'll spend the next 35 minutes looking at what is trying to be optimized and why is it failing here. Just to give you some feeling for some of the error messages or warning messages that you might see when you look at the CPU profile of JavaScript. All right, so some JavaScript basics. JavaScript is dynamically typed. That means the type of your variables can change all the time. Most scripting languages are dynamically typed. The opposite is statically typed, where your types cannot change, and they're always the same. If you think about C++ or Java, you always have to make very clear what type your variables are. You have to say whether it's an integer or a string, or if they're an object, you have to say exactly what class was instantiated to create this object. In JavaScript, there is no such thing. You say var or let or const, and do something, and you can also change the type that this variable has all the time. And by types, I don't only mean the basic types like ints and strings. I also mean the type of objects, of more complex objects. So if you have some JavaScript code like this, simple object, one question that would be important for a compiler is to know what are the properties of this object. And clearly, X and Y are the properties, but then there's also a bunch of other properties that you get from the prototype chain, which can change all the time because you can change the prototype. And even if the compiler knows, okay, these are the properties of the prototype chain, of course, you can change the properties all the time. You can delete properties that were on there, you can add more properties. So if the compiler sees the declaration of this variable, it has no guarantee later on when you're using the variable that it still has the same properties. Instead, only at runtime, at the point where you're using the variable, does the compiler know, by inspecting the object, what exactly are the properties. And so this dynamic typing makes it very hard to compile JavaScript into machine code that runs really fast, because there's so many options of things that could happen that if you compile this ahead of time, you just won't get any performant machine code that then is executed. So what all modern JavaScript engines do is just-in-time compilation. We are compiling just in time as we're using the function. That's sort of the opposite to ahead-of-time compilation, AOT. If you think about C++, you clearly do ahead of time compilation because it's a separate step from running your executable. You write your code, you save it, and then you say gcc-03, and it compiles it into an executable. Depending on what you're writing, that might take quite some time. And once that is done, then you have an executable, and as a second step, you execute that executable. It's not happening at the same time that you compile and run. In JavaScript, that's different. I mean, for once, there's only one step to execute it. If you think about Node, you're not first compiling. Well, sometimes you're transpiling from Babel or something, but that's not about compilation into machine code. But it's all happening at once, and in fact, we run machine code, and then we recompile, and then we run again. And we need to do that because up front, just from looking at the source code, it is very unclear what could happen to things like properties because of this dynamic typing. So your typical compiler pipeline looks like this. You have a parser that's generating an AST. You generate bytecode, and then the compiler compiles this bytecode into machine code, which you can execute. In JavaScript, if you care about performance and you're not restricted to the tiniest little IoT device, the JavaScript engines have just-in-time compilation, a JIT compiler. So from machine code, you execute machine code, and then you go back and compile some more, and you get different looking machine code, and you run that, and then you might go back again. So there's this loop between execution and compilation. Okay, so that's sort of high-level just-in-time compilation. And I want to look at a concrete example and how we actually make this faster. So what we're going to look at is property access, because it's all over the place in JavaScript. So it's used really a lot, and it makes sense to speed this up. You do property access all the time. By property access, I just mean get a property on an object. So I have a function called load. It takes a parameter object, and then it accesses object.x. In reality, you'd never put that in a function. I just wrote it so that my examples are a little cleaner. So object.x is everywhere, even if you just do console.log. Console is your object, log is a property. You're doing the .x all the time. And it looks super simple, we're doing it all the time, but if you think about it from a language point of view, there's actually a lot that can go on. So first of all, object.x, if you have a regular object and it has an x, it'll just return the value of that property. But there's a lot of other things that can happen. This could throw a type error. Nobody is preventing you from passing in null or undefined. It could return undefined because object might not have this property x. It could also be that object doesn't have an own property x, but somewhere up the prototype chain there's x. So you have to make a recursive lookup up the prototype chain. Object might be a proxy, so anything might happen with the getter trap. And then the x might have been defined with an accessor descriptor, so you have this get function, and that can have any arbitrary side effects anywhere in your program, whatever you tell it to be. So it looks super simple, you do it all the time, but lots of things could happen from a language point of view. And in fact, if you look at the ECMA script specification for object.x, so it's called a ordinary get. I don't want you to read all this in detail, I just want to give you an idea. It's like 8 steps just to do object.x, and even hidden in there is this recursion for the prototype chain. So if you're a compiler and you need to be spec compliant, which we try to be as much as possible, you have to do these steps, otherwise you just wouldn't compile JavaScript. So this is highly complex, and it's happening all the time, so we need this to be fast. Otherwise, we would never get anywhere with opening a React page or something. Okay, so what we do, let's talk through this. So here's this very complex load function, and I'm calling it with a simple object literal that just has one property x, and it's an integer. Now, when I call this the very first time, well, the compiler doesn't know anything about this object, so what it needs to do is follow the steps outlined in the specification. It needs up to 8 steps, or maybe look up the prototype chain. Okay, and so once we've done that, we figure out, okay, for this particular object, it's a regular literal, we didn't do anything to the prototype, the value of x, I get the value of x by just taking the value that's in the first offset internally of this object. So internally in V8, this object literal, the x value is saved at some offset in there, and that's always, yeah, so this is how we can then get the property once we figured out it's not undefined, it's not throwing, it's not the prototype chain we have to look at. And so now that we figured that out, we save this information and put it in a cache. And this is kind of crucial. We're not saving this particular object and the value 5. What we're saving is the shape of the object and a shortcut where to find the value. Does that make sense? So in the cache, I don't put x5 returns 5. I put something that looks like this object, so simple literal with only x in it, and then what the value of this key is the shortcut, the offset 1, because this is where the value is. And we associate that cache with this one call side. So basically a line of code or a part of a line of code if there are several property accesses in there. So every call side has its own cache where we save how to get to the property fast. So if we run some more code and we do another load, now with a different object where x is 17, once we get to the call side of this property access, what we first do is we check the cache. We say, hey cache, do you have a key for an object with an x? The 17 doesn't go in there, just something that looks like this. And the cache says, well, sure I have, just take offset 1 and return that, that's the answer. So we can skip all these steps and instead just have to do a quick cache lookup and then whatever the shortcut is in there. Okay, and so these caches have a special name. They're called inline caches, often abbreviated as IC. As I just said, every call side has its own IC. So even though this is within the same functions and it's both times object.x, since it's not the exact same call side, they have two completely independent inline caches. And the cache is a map of shape of object and shortcut to the value. Not the object itself, not the value itself, but the shape of object and shortcut to the value. And shape of object, this is an internal in V8. We also call it map or hidden class, but it's not part of the JavaScript standard. This is just what we do internally to speed things up. We assign to everything a map, and this lets us compare if two things are the same. In JavaScript, you don't have classes, or you didn't have them until ES5, but even now that you have them, they would not correspond to the same thing because we need to know that something is really exactly the same behind the scenes and not that you change something later on to this class. But yeah, it's a little bit like objects of a class. So this is a good abstraction. This is also why it's referred to as a hidden class, because it's not visible, but it's sort of like the class of objects. And two objects internally are considered having the same map if the way they were built is really the same. So they need to have exactly the same properties, but they also must have been added in exactly the same order. So lots of things are not having the same map, even though they might look similar to you. In particular, once one object has one more property than the other, they are not having the same map. If you ever want to dig into those little details, you can figure out if two things have the same map. You can use an intrinsic or an internal function, as we call them, have same map. Just take two objects, put them in have same map, and it'll be true or false. The have same map here obviously is not regular JavaScript, and you see I'm calling it with a % sign in front. So that's a V8 thing. We have a bunch of internal functions that you can call from JavaScript with this weird syntax. And if you want to do that, you have to call Node or Chrome with the special flag allow native syntax. That gives you access to all these internals. So if you want to play around and figure things like that out, that's what you can use. Okay, so the inline caches for things like a property access, which we do all the time, is something that helps us to save a lot of time. Because instead of doing this long steps that we have to do according to the specification, we remember what kind of objects we have seen and a shortcut on how to get the answer then. But just the inline cache does not give us enough performance for these massive JavaScript frameworks that we need to run. So into play comes an optimizing compiler. All the bigger engines have at least 2 compilers. You always have a baseline compiler, and then you have 1 or more optimizing compiler. And the way this works is you start off compiling your JavaScript with the slower baseline compiler, and the baseline compiler keeps track of which functions you're using a lot. And once it identifies a function as hot, as being run all the time, it's deciding that the optimizing compiler should recompile this function into better machine code with the information that we gathered while we ran it. So when you keep executing it lots of time, it saves you time. Does that make sense? You start everything slow, you keep track of what is being used a lot, and if you've identified hot stuff, you say, okay, do some more work compiling it, but then what I get out of it is really fast. And our optimizing compiler, some name dropping, it is called Turbofan. We still have one which we're in the ways of retiring that is called Crankshaft. So if you've seen Crankshaft or Turbofan in any optimization profiles, that is our optimizing compilers. And if we combine optimization with these inline caches, this is what's giving us really a lot of speed. And I would like to show you, if you're still awake after all this dinner and beers, how exactly that works. So let's skip the high-level talk and get to the nitty-gritty details. So the load function, I'm calling this a bunch of times, and I'm always calling it with the same map. So it's not the exact same object. I mean, 4, 2, and 7, and 9 is obviously not the same, but all these objects are objects literals with an x and a y. So when I'm calling this function all this time, we're building up this cache, this inline cache. And there's only one kind of shape of object this map has seen, so we have one key value pair in our inline cache. So assume I'm calling this function a lot, like I think 3,000 times. That's when the compiler decides this is a hot function, we need to optimize it. And now the optimizing compiler is recompiling the load function using the information in the inline cache. And then this is what you get out. And I think it's super cool. So this is machine code for this optimized load function. I think it's super cool that if you do web stuff and high-level JavaScript and it's all running somewhere, you could still go all the way down to what's happening to the registers in your machine. And I promise you will make sense of that. So it might look like a lot of code, but considering it's machine code, it's really little. We're starting up here with a call stack check. That is when we enter the function. We just have to make sure we have space for a frame stack before we enter the function. So now we're inside load. And then we do check non-smi. Smi is V8 speak for small integer. Internally in V8, everything is either a small integer or it's a heap object. So anything that lives in JavaScript, since it needs to be garbage collected, we put it on the heap and keep track of it. And we just need to make sure that the parameter that you passed into load, that is internally not a small integer, but an actual object. So we check real quick, is this an object? And now we do the check maps. Maps is our language for hidden class, shape of an object. So here we are checking the shape of the parameter that was passed into the function. And we're checking it against the one shape that we had in the map, that we had in the inline cache when we were collecting feedback before. So you call this function with a parameter, and this code here is checking whether your parameter looks similar to the other parameters that we have seen. And if that is the case, if we found that in the map, then we just do the shortcut that was the value in the map, which in our case is just a load named field. It was at offset 1 where we can get that value, and we are done with it. So this is like 4 steps in like tiny little machine code instructions compared to 8 instructions in the specification that had recursion and arbitrary side effects. This is why we get so much performance improvements by doing that, because this is really no work compared to an actual property lookup. I said we're comparing these maps. Of course, nobody is forcing you to always call load with the same kind of objects. So we check the maps, and if what you passed in doesn't correspond to anything in the cache, that's when we say, oh, okay, let's jump, in this case, jump down here to 91. And 91 says, deoptimization bailout. So what we looked at was the code from the optimizing compiler. If our object doesn't match what we've known from when we filled up the cache, then unfortunately we have to deoptimize and bail out here. We can't use this really cheap, fast code. Now we have to do all the 8 steps and like work through it until we have the property. Okay, and so for inline caches, what we care about is a lot what state they're in. So they can be uninitialized if we haven't gotten to them yet, if they don't have anything in them yet. And then we like our caches to be monomorphic, one morphic shape. So if there's only one single shape you've seen, then the cache is monomorphic. There's a single entry in there. We are still okay with polymorphic, poly-many. In our case, that's up to 4 entries. So if you've seen 2, 3, or 4 objects with different shapes, like one had an X property, the other has a Y, and the others have X and Y, for example. That would then be 3 shapes, and if your cache has seen them, then it's in a so-called polymorphic state. And then there is megamorphic. That's when we have more than 4 entries, but it's a little different from the mono and polymorphic case. The monomorphic and polymorphic cache is for that one call site, so for this one single point in your code where you say object.x. The megamorphic cache is for your whole application. It holds up to 3,000 entries, but it's shared by everything that goes into an IC. So in this example here, where I always called load with the same kind of objects, it's monomorphic because there's one map in there, and when we were looking at the machine code, there was one single map check in there because I only have one entry in the cache that I need to compare against. When I call this function with different objects, so what's different here is it's A, B, C, and D. It's not always Y as the second parameter. So for the compiler, this is considered something completely different because for the first object, if you want A, well, just look at the second offset. But for the second object, if you want A, if you check the second offset, that would be wrong because that's where B is. So those are very different internally from what a compiler thinks. So we get, I'm doing this with 4 different things. So I have 4 entries in my cache. So I consider this cache polymorphic. And if this is in my cache, when the optimizing compiler starts to compile, then the machine code looks a little different, and it has 4 map checks now. So this is the relation between monomorphic IC and polymorphic IC. We have a different number of checks in there. So again, we are checking, is the object that I passed in, does it correspond to the first map or the second map or the third map and so on? If it matches one of them, we jump down to here where it says, oh, just do this shortcut and always return the value at offset 1. If it doesn't match either one of those 4 entries, then we say, okay, bailout, we can't use this optimized code, please do the slow path. Okay, and if you want to try this out for yourself, this is, you can always pass in flags to Chrome or to Node. So you just have to pass in print opt code and -- code comments to get a few of these comments between the opt code. So if you really want to see what's going on, write a little script and then try this on it, change the script and see if it corresponds to your intuition. Okay, and since we cared about the inline caches, so here it was polymorphic, which meant instead of these 2 lines, the map check and the moving, we now have to do 4 times 2 lines, so that's more instructions, so it's obviously slower than the monomorphic case. So for performance reasons, we care about what the state of our inline caches are in. And you can figure out what the states of your ICs are by doing -- trace IC. So again, another flag that you pass to Chrome or to Node, and then you get this wonderful non-intuitive printout of what the ICs are. So you see here string X, that makes sense because we were getting object.x. And on the left, you see the states that your inline caches are transitioning to. So 0, 1, P, and N for uninitialized, mono, poly, and megamorphic. And so you see here on the left, when we first started, it's uninitialized, it has never seen anything. Now we're hitting the first entry, put that in the cache, so you go from dot to 1, which means from uninitialized to mono. As we call load again, now with a different object, we have 2 entries in the cache, so we go from mono to poly and so on. And if we keep doing that for more than 4 times, eventually we'll go into megamorphic. This is very hard to read, and that was only for the tiny little toy example. So in a real app, you would not want to look at this output, and you can use ICE, the IC Explorer. It just gives you a nicer way to filter and sort your results. So here's a more real application. So you have 1 million entries. You would not want to dig through that in the console or with your text editor. This one here nicely groups it together. So you can filter, for example, by function name. This is this isRelated2 function that we saw at the very beginning with the exclamation mark, and we can now figure out exactly what is happening in this function, what are the inline caches, when are they changing state, and so on. So we have this example. We run the function a few times. The cache is filling up. It's in monomorphic state. Now the optimizing compiler decides this is a hot function. Let's optimize load. It's optimizing it. It's writing out this machine code by using the information that was in the cache. And now we come again and we call load with a completely different looking object. So what's happening now, unfortunately, is this will cause us to deoptimize. This is exactly that case in the machine code. We did a map check against this one map that was in the cache, and that failed, so we have to jump down to bailout deoptimization. So that means we can't use that optimized code. In fact, the compiler is throwing it away because it says, well, this code doesn't work. Apparently, we're getting other stuff than what we got in the past, so this optimized code doesn't work. Let's throw it out, and let's do all the slow, correct steps to figure out what these properties are. And you can always figure out which functions are being optimized and when or if they're being de-optimized. So again, to Chrome or to Node, pass in the flags traceopt or tracedeopt, and it'll tell you what is being optimized. So you see here at the top, compiling method, JS function load, optimizing load. And then sadly, down here, you see evicting the optimized code for load because we had to de-optimize. We were calling it after it was optimized with something that was not expected at this point. So back to this original problem of the warning symbol, I hope this gives you some idea of what this message means and where it's coming from. So what's happening here is we're calling isRelated2 with some parameter, and there is property accesses in there, so there's an inline cache, and with the parameters that we're calling this function, the inline cache is being filled. After a while, the compiler says, oh, let's optimize this hot function. It's using the cache, and we keep running it, but we throw some parameter in there that's not found in the cache, so we de-optimize. And then we do this, then we run the slow code again until we realize, okay, isRelated2 is hot, let's compile again, let's optimize, and then we run and we de-optimize again, and we do this 10 times altogether, and then the compiler says, stop, this function is being called with like stuff all over the place. It's not useful if I keep optimizing and throwing that away. So at some point, the compiler says there's too much randomness in the arguments to make it useful to generate optimized code and just gives up on that. So this is like V8 internals because of dynamic typing. We have just-in-time compilation. We have optimizing compilers. And if you feed different stuff to them, it might cost them that they have to bail out from the optimization and start over again. And if it just never works, then a compiler gives up here. So by looking at the GPU profile in DevTools, seeing some functions that are problematic in terms of performance, and then by looking at the inline caches, by looking at the optimized machine code for that, and of course by looking into the actual source code, it's possible to make some changes so that this is related to will not be optimized, deoptimized, optimized, deoptimized all the time. So with a few changes, you can get it to do that, and then if you profile again, you don't have the exclamation mark anymore. Okay. Little side note, if you've looked into the CPU profile before, you might have seen not optimized because of a try-catch. Anybody seen that? Okay, so we fixed that in our new compiler pipeline. Try-catch is not a problem anymore. This is not causing the compiler to de-optimize every time there's a try-catch in there. Maybe I should have said this at the beginning, but obviously be very careful with your optimizations. Don't optimize until you must, unless you must if you have no points, if nobody is telling you, or if you don't have measurements that your app is too slow. Don't optimize, it'll just be performance that suffers, readability that suffers. You might introduce bugs, you make it harder for your coworkers and yourself. And if you do need to optimize, measure first so that you really identify the points that are causing problems and then speed those up. What I was talking about is really low-level stuff. Unless you're doing tons of calculations in JavaScript, this will never be an issue. I mean, if you call a function only a few thousand times, it doesn't really matter to the end user which machine code you're executing. Like, it's most likely that images or compression or which resources you load, that those things make a much, much bigger difference than some tiny little things that's causing an optimization or de-optimization. But if you do identify that that's your problem, then you still need to be careful because everything I talked about is V8 internals. It's not written in the specification. It's how we do stuff today. That might change at any time. It's not, I mean, there's no contract to the outside that we have to use ICs or that polymorphic caches can have at most 4 instead of 7 things in them or something like that. We can change it all the time if we have data points or heuristics or other ideas. So if you optimize to anything of that and we release Chrome Canary tonight, it might actually be that your code is slower now because we changed internals. And obviously, this is very different in the other engines. So in Chrome, in the web, you never know which browser is the end user using. They use different engines. And even if you do have a Node application, you might want to switch out the engine to Chakra Core, or Firefox is also working on Spider Node. Don't dig your own grave by optimizing for the internals of one engine. Like, it'll most likely not turn out well in the end. But I hope I was able to give you some overview that's clearing up a little bit this magic black box of a JavaScript engine that is making your source code being from letters to something dynamic and great that's running. And if you want to dig deeper into this, if you want to play around with it, there are several flags that you can use. So there is the trace opt, trace deopt, that just tells you which of my functions are even being optimized and when are they de-optimized. It usually also gives you a reason. You can do a trace IC to see, well, is my app having problems with lots of polymorphic caches? What's happening here? And if you really want to get down to it and look at the machine code and the actual instructions, you can do print opt code. You can all do this with Chrome. You just start Chrome from the console and put a --JS flags equals and then the v8 flags behind it. If you have Node installed anyways, just use Node. In Node, just make sure you put the flags right after Node and not after the script that you're calling. If you really want to get down to it, you can use D8. That's the debugging shell of V8, but that requires you to check out and to build V8, which it might take some time. It's just some extra steps. But the advantage of D8 is that the debug output that you get is really just for the code that you're running. If you put these flags after Node process, of course, you also get tracing for all the Node internal boot up or boilerplate code running before your thing. And if you want to look at the inline cache, at the states of that, in a nicer way rather than on the shell, then you can use the IC Explorer ICE. It's distributed with V8, and there's a link in here. So I hope I was able to give you a little bit of understanding what's going on. And if you have questions, then talk to me at the party tonight. Thanks.